In the following video, we'll be looking at an application of the law of definite proportions to figure out formulas of hydrates and formulas of organic compounds through a process referred to as combustion analysis. So we'll start with hydrates. So you might recall from the second unit that a hydrate is really any ionic compound that, when it's crystallized from a water solution, often has water molecules incorporated into that crystal structure, which is what forms a hydrate. Hydrates will have a specific number of water molecules chemically bonded to each formula unit or to each ionic compound. So if we look at the following example of Epsom salt, which is magnesium sulfate, the hydrate. That magnesium sulfate, so we find one compound or one molecule of magnesium sulfate. So we have our magnesium, we have our sulfate molecule, and then associated with that magnesium sulfate are a total of 7 waters that more or less surround the molecule. And they are interacting with the molecule. They're not covalently bonded. They're not bonded ionically. So it's more of an association. So with one magnesium sulfate, we have 7 waters associated with it. So again, what that's telling us is that for every formula unit of magnesium sulfate, we have 7 molecules of water. And we know we're dealing with a hydrate when we encounter a raised dot in the chemical formula. And that raised dot will be in front of one or more water molecules. And this is going to denote that hydrate compound. Now, compounds that have no water incorporated into them, or more specifically, ionic compounds that have no water incorporated into them, are referred to as being anhydrous. So they are without water. So, for example, the compound calcium sulfate is referred to as anhydrous calcium sulfate to indicate that there are no water molecules associated with this compound. Now, we care about hydrates because the molar mass of a hydrated compound, when you're calculating that molar mass, it must include the mass of any water molecules that are in the compound. So we'll have a look at the following example dealing with hydrates. So in example 1, we have a 50.0 gram sample of the hydrate contains 27.2 grams of barium hydroxide. We're asked to calculate the percent by mass of water in barium hydroxide XHO2 and to find the value of X. So there's 2 parts to this question. We're being asked to determine the percent by mass of water, and we're being asked to determine the value of X. So how many water molecules are there? So we'll start first with the mass percent of H2O within the compound. And when we're calculating this, there's a few values that we have and that we know. So we know that we are dealing with the mass of the hydrate. Even though we don't know what X is in this compound, it doesn't matter. We know that the total mass of the barium hydroxide plus water is a total of 50.0 grams. We're also told what the mass of the barium hydroxide alone is. So in this case, the mass of barium hydroxide, we're told directly in the question that this contains 27.2 grams of this particular compound. Now, if we want to find the mass of H2O, given this information, all we have to do is take the mass of the hydrate, so the mass of that barium hydroxide, XH2O, and subtract the mass of just the barium hydroxide alone. And this will give us the mass of water within this compound. So when we subtract those two numbers, we get the mass of water being 22.8 grams. Now, to figure out the mass percent of the water, now that we have the mass of the water, we know the total mass of our compound. So for that mass percent of H2O, it's simply going to be mass of H2O divided by the mass of our hydrate. We don't know what X is still, but that's okay. It doesn't hold us back from doing this calculation. So it's a matter of subbing in the numbers that we have. So that 22.8 grams divided by the 50.0 grams multiplied by 100. And this will give us a percentage, when we take into account sig figs and round accordingly, a mass percent of 45.6%. We can say, therefore, mass percent of water is 45.6%. Now, in the second part, where it asks us to find X within that formula, that barium hydroxide XH2O, we can use some of the information that we have already to go about figuring out what X is in this case. So we can use mole ratios between the number of moles of barium hydroxide and number of moles of water to figure out what that X value is. Because we know for every 1 molecule of barium hydroxide, we'll have a certain number of water molecules associated with it. So we already know the mass of barium hydroxide. This comes directly from the question itself, 27.2 grams. From the previous question, we already calculated the mass of the water as being 22.8 grams. Since we have masses, we can take those masses and convert them into number of moles of each compound. So in the first part, we need to identify the masses of each compound that we're dealing with. In the second part, in answering this question, we'll then convert grams into moles for each of our compounds. So we'll start with the barium hydroxide. So the number of moles of barium hydroxide is going to be equal to the mass of the barium hydroxide that we have, at 27.2 grams, divided by the molar mass of barium hydroxide, which is 171.35 grams per mole. When we calculate number of moles, we get 0.159 moles of barium hydroxide. Don't worry about significant figures and any of that stuff. We'd like to carry as many decimal places as we can. And then we'll need to determine the number of moles of water. So we know the mass of our water is 22.8 grams. To figure out the number of moles, we'll divide this by the molar mass of water, the 18.02 grams per mole. And this will give us total number of moles in 1.26 moles of water. Now, to figure out to figure out what X is, we just need to do a mole ratio between number of moles of barium hydroxide, number of moles of water. So in that third part, we'll do a mole ratio. So we'll look at a mole ratio between number of moles of water and number of moles of barium hydroxide. Once again, like when you're setting up your mole ratios, because we want whole numbers, we want to put our big number in the numerator and put your smaller number in the denominator, and this will ensure that you get a whole number and a number that is not a decimal. So in this case, we have 1.26 moles of water, which we just calculated, and we know we have 0.159 moles of barium hydroxide. When we do that ratio, we get something along the lines of a ratio of 8 to 1, meaning that we have 8 molecules of water associated with 1 barium hydroxide. So based on this ratio, we can therefore say that our formula is BaOH2, with the raised that, 8 H2O. In the next part of the note, we'll have a look at a process referred to as combustion analysis. Combustion analysis is used for determining empirical and molecular formulas of organic compounds. So before we get into it, just a little bit of background about combustion analysis. So a large number of important chemicals are composed of hydrogen, carbon, and oxygen. With the combustion analysis and with carbon-hydrogen combustion analysis, this is actually useful for analyzing these types of chemicals. It allows scientists to determine the percent composition of compounds that are made up of carbon, hydrogen, and oxygen. This analysis can also be used to find the empirical formula of a compound that contains carbon, hydrogen, and oxygen as well. And we call it combustion analysis because we are taking our organic compound, so our compound that contains carbon, hydrogen, and oxygen. We know it contains those molecules, and it can contains those atoms. We know it can contain other atoms as well. But generally speaking, we'll be dealing with carbon, hydrogen, and oxygen. So carbon, we don't know the amount of carbon that we have, so we'll just label it as a subscript X. Hydrogen generally will be a different amount, so we'll just give that a subscript Y. And then oxygen, different amount of atoms in there, so we'll give that a subscript Z. So in general, we'll deal with the compound CXHYOZ. From the last unit, you know that when anything containing carbon and hydrogen undergo combustion, and combustion has to occur in the presence of oxygen, this will predictably always yield carbon dioxide and water. Now we can use the products of this combustion analysis, the carbon dioxide and water, to figure out what our subscripts are. So this will always generate X amount of CO2, and will generally generate, won't always generate Y amount, but we'll call it Y amount of H2O. And so using the products of this combustion analysis, we can actually determine what amounts of carbon we have, what amounts of hydrogen we have, and ultimately what amount of oxygen. So all of the carbon that is generated and goes into the CO2 is coming back from the carbon in our original sample. The hydrogen that is generated in H2O, all of this is coming from the hydrogen that we have in our original sample as well. The only tricky part is that the oxygen that we generate, we don't know the source of that oxygen. If we have oxygen in our original compound, that oxygen could either come from the oxygen gas itself or the oxygen within the compound. So we have a slightly different method of figuring out how much oxygen we're dealing with when we're doing this type of analysis. So let's have a look at the first example question. So In the first example, we have a 23.04 gram sample of a compound containing carbon, hydrogen, and oxygen. This is subjected to combustion. So we're taking our compound, we know it contains carbon, hydrogen, and oxygen. It's being burnt. Now the product from that combustion, so from that the products from that combustion we know are going to be carbon dioxide and H2O. And we're told from this combustion we produce 44.01 grams of CO2 and we produced 27.03 grams of H2O. And we're asked then to calculate the empirical formula. So using these products of combustion, we can start to figure out how much carbon we've generated and how much hydrogen we've generated. So in the first thing that we're going to do within this question is we are going to determine the number of moles of carbon that we have in carbon dioxide. So we know the mass of CO2 that we are starting with, which is 44.01 grams. We are going to have to figure out how many moles of carbon dioxide we have, and so before we can do that, we need the molar mass of CO2, which very conveniently is also 44.01 grams per mole. So when we go to calculate number of moles of CO2, we'll simply take the mass of CO2, we'll divide it by the molar mass, and we'll get number of moles of CO2. So that's equal to 1 mole. So now that we have number of moles of CO2, we need to figure out number of moles of carbon that we have. So to figure that out, we just need to look at the chemical formula. So in CO2, we only have 1 carbon for 1 CO2. So if we have 1 mole of CO2, this should be equal to the same number of moles of carbon. So since we have 1 mole of CO2, we can say that we have 1 mole of carbon in our sample. So we'll work through the next element with hydrogen, and we'll figure out how many moles of hydrogen we have in H2O. So same method again. We know our mass of water that was generated, 27.03 grams. We know the molar mass of water as well. We can calculate that easily at 18.02 grams per mole. And so we can use these numbers now to determine number of moles of water that we have. When we do this, we calculate that we have 1.3 moles of H2O. It's important to distinguish the fact that we have this many 1.5 moles of H2O. This is not the number of moles of hydrogen. We need to now calculate how many moles of hydrogen we have. We know that from the formula, we have 2 hydrogens in every 1 molecule of water. So if we have 1 molecule of water, we have 2 atoms of hydrogen. If we have 1 mole of water, we then have 2 moles of hydrogen. So number of moles of hydrogen is equal to 2 times the number of moles of water that we have. So in this case, because we have 1.5 moles of water, we'll multiply that 1.5 moles by 2, and this will give us 3 moles of hydrogen. Sorry, just changing views, making more room. So we know the number of moles of hydrogen, we know the number of moles of carbon in our sample. The third element that we need to figure out before we can start doing some mole ratios is determining number of moles of oxygen. So determining number of moles of oxygen, we can't just go back and look at our chemical formulas for carbon dioxide and water and add them together or anything like that. That's not going to work. Remember, we don't know where the oxygen is coming from in the CO2 and within the water, if it's from the compound or from oxygen. So to figure out how much oxygen that we are dealing with, we got to remember that with our compound, which is made up of carbon, hydrogen, and oxygen, we know the quantity of carbon, we know the quantity of hydrogen, and from that we should be able to determine how much oxygen is present. So from the original information given to us in the question, we're told that we have 23.04 grams of this particular sample. So we know the mass of that sample. So if we know the mass of the sample, then we should know that the mass of carbon plus the mass of oxygen plus the mass of hydrogen, plus the mass of oxygen should add up to this total mass as well. And then that is a number that we can start working with and using. So we have to go back to our calculations that we just did in terms of finding number of moles of carbon, number of moles of hydrogen, and we can work out the mass of carbon and the mass of hydrogen that we have within our sample. So in terms of figuring out mass of carbon, we know that we have 1 mole. If we multiply that by its molar mass, at 12.01 grams per mole, in this sample of carbon, the mass of carbon is 12.01 grams. With hydrogen, we know that we have 3 moles of hydrogen. So if we take those 3 moles, we multiply it by the molar mass of hydrogen, the atom, that's what we're dealing with, we'll get a total mass of hydrogen as 3.03 grams. So if we know the mass of our sample, we know the mass of carbon, we know the mass of hydrogen, we can use that to determine mass of oxygen. So it's a matter of just plugging in numbers in this case. So the mass of our sample we know is 23.04 grams. This is equal to the mass of carbon, which we just determined, being 12.01 grams, plus the mass of hydrogen, which we just determined to be 3.03 grams, plus the mass of oxygen. So when we rearrange and solve, we can determine the mass of oxygen as being 8.0 grams. In this case, I guess we'll go 2 decimal places, being 8.00 grams. So now that we have a mass of oxygen, we can now start figuring out number of moles of oxygen. So we can take the number of moles of oxygen, we can take our mass of oxygen, and we'll divide it by our molar mass of oxygen. In terms of number of moles of oxygen, we should get 0.5 moles. Alright, so all that work was just doing to get number of moles. We've only kind of just begun our calculation. So once we have number of moles of oxygen, number of moles of hydrogen, number of moles of carbon, we can now set up some mole ratios. So we'll look at carbon, we'll look at hydrogen, and we'll look at oxygen. And so when we're setting up our ratios, remember we identified the thing with the least number of moles. So in this case, it'll be oxygen at 0.5 moles, and we divide everything by that number. So in terms of carbon, for our mole ratio, we know that we had 1 mole of carbon. We divided by the 0.5 moles for oxygen, and we end up with a ratio of 2. For hydrogen, we had within our sample 3 moles divided by 0.5 moles. This will give us a total of our ratio of 6 to 1. And our oxygen, we know we had 0.5 moles divided by 0.5 moles, and it will give us a ratio of 1 to 1. So these numbers that we've now calculated are the subscripts that we have within our formula. And so we can now use this to construct our empirical formula. So we get an empirical formula. So therefore, we get an empirical formula of C2H6O. And this is our empirical formula using combustion analysis. Now, in the following example, I'll let you guys work through this. In part A, it asks you to determine the empirical formula of the compound. When you do this calculation, you should get C1, I'll use subscripts 1, you should get CH2O, and it then asks you to determine the molecular formula of the compound. This is done in the same manner that we talked about in the previous lesson, and in terms of that molecular formula, you should get an answer of C6H12O6. And lastly, there are some practice questions at the end of the note. Please work through those, make sure that everything is okay. And then there is some additional homework questions related to hydrates on page 278. Please do numbers 51 to 56.